All right, it's time. Welcome back to everybody. Today's really our last day of, ordinary class. We have our test on Friday, and then the final exam, and that'll do it. I am going to say a little bit towards the end about the test on Friday, but maybe we can just get into the very last topic is minimum spanning trees, or minimal spanning trees is what I called it last time. Minimal spanning trees. I'll refresh our memory about what a spanning tree is for a graph. So any graph, actually, every graph has a spanning tree. And they are, if all you want is just any old spanning tree, they're typically easy to make. So this graph here has many different possible spanning trees. And remember, a spanning tree is a tree which meets every vertex in the graph. So in this example, I'll draw them with my thick red edges, something like this. That is a spanning tree. It's a tree which meets every vertex. So it's a tree, and I hope you remember, a tree means a graph sort of inside the larger graph with no loops in it, which meets every vertex, right? That, what I drew over there, is a spanning tree because it touches all the vertices of the original graph. Spanning trees come up in, like, the examples that I gave last time would be like if each vertex in this picture is like, a house in a neighborhood, and you need to wire up all the houses with electricity or water pipes or anything like that, then the way in which you wire them up ought to be a spanning tree, or the way in which you connect them with pipes. Pipes are meant to make sort of tree-like shapes. They're not supposed to have loops in them or anything like that. So this is, this is sort of a random arrangement. In real life, such a picture. In real life, if you were really laying down, water pipes or something, it's much more likely that they would just do it like this maybe, or something like that. This is a more sensible way to do it. This is just another spanning tree in that same graph, right? Every graph, generally, any given graph will have many, many different ways to make a spanning tree. This is unlike, say, Hamilton circuits, where many graphs don't have a Hamilton circuit at all, and some which do would have only one or two or something like that. But as far as spanning trees, every graph has a spanning tree. And typically, a typical graph has many, many different ways that you could make a spanning tree. All right. Now, we are going to talk about minimal spanning trees, because every graph has many different ways of making a spanning tree. If you're trying to do this in real life, you want to do like somehow the best spanning tree, where if you're say laying down water pipes or something, the best one would be one which has the shortest total distance of pipes that you have to use, or something like that. All right. So we are interested in how to find the minimal, meaning like shortest total length or something like that, the minimal spanning tree in a weighted graph. For example, I actually made this. This is not so hard to copy down, but I put it on a handout for us all. So here is a weighted graph. I gave you 2 copies of it just in case some disaster happens, although these ones are fairly straightforward to work out without messing it up. Come on now. All right. How to find the minimal spanning tree in a weighted graph. So I have this picture also. There's a bigger, fancier one on the back that we'll get to. I would like to find, of course, like I said, there are many different ways to make a spanning tree here. Everybody got one? All right. To find the minimal spanning tree, that means a spanning tree with the total weight sum as low as possible. This is very similar to the traveling salesman problem, but it turns out this is actually much easier than solving the traveling salesman problem. So to find a MST, that is minimal spanning tree, we can use the same procedure from last time, the same sorted edges algorithm. The sorted edges algorithm. So this is what we did last time for finding Hamilton circuits, but the same thing will work for finding minimum spanning trees. And the way it works is you choose edges in order, starting sort of lowest to highest weight. This is exactly like we were doing last time. You choose edges in order, starting from the lowest to the highest weight, and you just have to make sure as you go, you are never allowed, in a Hamilton circuit, you're never allowed to have a three-way intersection, and you're never allowed to make a sub-circuit. Now, spanning trees, the big difference, and I said this at the end last time, of course, in a spanning tree, you are allowed to have three-way intersections, right? They happen all the time. But you definitely are not allowed to have a sub-circuit because it has to be a tree, and a tree is not allowed to have any circuits at all. So the rules for doing this sorted edges for spanning trees, choose edges in order starting lowest to highest weight, and never make any circuits, sub-circuits or big circuits or whatever. No circuits allowed. Three-way, okay. Right? It is not a problem when you're making a spanning tree to have three-way intersections, but it is a problem if you ever make a sub-circuit. All right? One last thing about minimal spanning trees is you just have to, I will say, stop when you're done. What I mean by that is once it meets each vertex. And you'll see when you're doing this, sometimes it is a little unclear if you're done or not, and you have to kind of like step back and take a look and say, am I actually finished, or do I need to keep on going, choosing edges? All right? This is really all that there is to it, the sorted edges procedure for minimal spanning trees. So let's just try and do it on this one here, and then the one on the back is a bigger one for you all to try. So what I'm going to do is look at the numbers here. Now, if you want to make sure that you really are looking very carefully at the numbers, you could write down a list of all the numbers in order, although in an example like this, I don't think that's really necessary. I am going to choose edges in order, starting from the lowest to the highest weight. So the lowest weights that I see are 4, and there are 2 edges with 4, so I am going to choose both of those edges. You can scribble them in, or you can use colors if you've got colors, whatever. If you're doing it by hand, I would just scribble on them like that. All right, those ones are the lowest available weights. Now we just continue with the next lowest weights. I see a 5. Can I, and you ask yourself, am I allowed to use this 5? Since I'm making a spanning tree, a 3-way intersection is allowed. A sub-circuit is not allowed, but this 5 doesn't make a sub-circuit, so I can choose the 5, right? The next lowest weight available would be the 6. What do you say? Can I use the 6 or not? I say no, because the 6 makes a circuit, so I'm just going to X that out. You cannot use the 6 here, because if I were to include that, it wouldn't be a tree anymore. It would have a circuit in it. Okay, next would be the 7. Can I use the 7? I say yes, the 7 looks great to me. It doesn't make any circuits, so scribble that one in. Next is the 8. What do you think about the 8? I say you cannot use the 8 in this case, because that, again, makes a little triangle there, which is not allowed. All right. What's next? The next number will be 10. Can I use the 10 there? The 10 is over here. I say no. That makes this sort of trapezoid-like subcircuit, this 4-sided thing. So the 10 is not allowed. Next I see a 12. Can I use the 12 there? I believe the 12 is allowed here. Going down this diagonal. Okay. Around this time is when you start to wonder, am I actually done? This is the step I said. Stop when you're done. Once the tree that you've drawn meets every vertex, that means you're done. And actually, I am done at this point. All of the vertices are now part of the tree at some point, and so I'm finished. Even if you didn't realize you were finished, the next step would be to consider the 13, but the 13 makes this circuit here, so you could X that out. And then I would consider the 20, but that makes this triangular thing, so I X that out. And now everything is either X'd or chosen, so I must be done. All right? So that's it. This is the minimum weight spanning tree. So my final answer, I mean, if you wanted to see it a little better, it looks like that, right? A little guy with no head, I guess. All right, this is my spanning tree. The great thing about the sorted edges procedure, this is good news. Good news for all God's children. The sorted edges procedure, and I don't really want to get into the details of this, but sorted edges for minimal spanning tree actually does find the best possible minimal spanning tree every time. This is not true of the sorted edges for traveling salesmen. If you recall, for the traveling salesman problem, the only way to guarantee the best possible answer is to do the brute force, which you basically never want to do in real life, except unless it's for very small examples. So in the traveling salesman problem, the sorted edges does not guarantee that you're going to get the best possible answer. It is, though, going to always give you the best answer for the spanning tree problem. And so if you talk to, when you're in the club talking about graph theory, the people will expect you to know that the traveling salesman problem is very hard to solve. This minimum spanning tree problem is viewed as very easy because you can just do the sorted edges and you get the correct answer every time. Versus the traveling salesman, you can do the sorted edges and it's easy to do, but you don't always get the best possible answer. All right, I would like for you all to turn the page over and try to do this bigger one on the back. It's a lot bigger, but actually it's really no harder. You just got to make sure you don't miss any of the numbers. So starting with the lowest number available and add the edges in, make sure you don't ever make a subcircuit. See what you think. All right, I'm going to do mine up here. I hope that you get the same answer that I do. It is easy to mess this up if you just miss one of the numbers. So I began by choosing the 14, and then the 15, and then the 16. Those are the lowest numbers on the whole picture. The next lowest number is 18, but that makes a triangle right here, so I am not going to choose the 18. Then the next lowest number I see is 20, which I can pick right there. The next lowest number I see is 22, but that makes this triangle here, so the 22 is not allowed. Next, I see 24, I guess. I'm going to take that one. Oh, I forgot the 19. Sorry. Although it's okay at this point. I can still just add it in. Even before I did the 20, I should have done the 19. But anyway, then I would do the 20, not the 22. Yes, the 24. I hope I'm okay so far. Any comments? No. All right. And then after 24 comes, what's next? 30? Yeah, I see two 30s. There's one 30 here which cannot be used because that makes this into a circuit. But there's a 30 over here, which I should choose at this point. Remember, when you're doing this, you should not be trying to make it into a tree, like the fact that I chose this edge way over here, which is not even connected to these other ones. That's okay. Eventually, it will become connected as a tree, but you don't have to force it just yet. Okay, so that was 30. Next, I see two 31s, and I think they are both legal at this point. So I'll pick a 31 and a 31. All right, next would be, there's a 36 over here, but this 36 makes a circuit here, so I'm not going to choose that. I see a 38, which would make a triangle there. I see a 39, which would make a circuit here, so I'm not going to do the 39. I see 43, that makes a circuit. 49 makes a circuit. 50 will do it, and I think that's the last. I think I'm done at this point, right? What we have now is a tree that meets every vertex, I think. I'm just going to thick it up just to be sure. All right. I think that does it. I hope that, so if you, if you did this correctly, you should have got exactly the same spanning tree that I did. Any questions about that? I hope this is what you got. All right, excellent. This is really it in terms of this is the last item on the checklist, the minimum spanning tree sorted edges. That's really all there is to it. And I think I am done with the new material. There's not any more to say about that. There also is a nearest neighbor for minimum spanning trees, but I don't think we need to get into that. If we had yet another extra day, we could talk about that also, but I'm satisfied. So I would like to talk a little bit about the test then. One very important announcement, which I'm actually very disappointed in myself about, and that is somebody informed me, or somebody asked me, which caused me to realize I have all semester long been telling you the wrong date for the final exam. I was off by one day. So our test is on Friday the 13th. I said it was Thursday the 12th, but it's Friday. I feel badly about this. I hope that you're not angry at me, but it's okay to be angry at me because I deserve it. So I'm going to write this down here. Our test, our final exam is Friday, December 13, 8 a.m., 8 to 11 a.m. If you look on the syllabus, like the printed out one that I gave out on the first day of class, it said Thursday, December 12th. I hope that this is not a problem for anybody. I understand that people make plans for leaving campus at the end of finals, although this is pretty close to the beginning, so I hope that it hasn't messed up any of your plans. But if this is a real problem for somebody, please let me know. And this is totally my fault, so I'm happy to help you out in any way that I can think of as far as if that date is somehow impossible for you to do, then please tell me and we can work something out. But yeah, this is the true final exam date and time, and it's going to be in this very room on Friday at 8 a.m. Any questions about that? I feel badly about this, and I hope that you will accept my apologies, and we'll work it out if there are any problems resulting from that. I also wanted to offer, I have 2 sections of this class, and for whatever like scheduling reasons or whatever, if you would prefer to go to the other final exam, that's totally fine with me. Although you may not like this one any better, but the other one, just in case, the other one is Tuesday, December 17th, so it's after the weekend at 11:30 a.m. I assume most of you would rather take the earlier one, but if I don't know, if you're quirky and you would rather stick around until Tuesday, you are welcome to do so. I mean, you should tell me ahead of time, but that's totally fine if you want to do that day instead. All right. Anyway, let's talk about the test on Friday. I thought I would just give us a little reminder about what's going to be on the test. Somebody emailed me last night and said, what's going to be on the test? And I mean, the simple answer is everything is going to be on the test, just like all of our other tests. Everything is always on the test. But I'm not sure what the person actually meant when they were going to ask. But anyway, I will just remind us of sort of the new ones which will appear on the test will be number 25 through 32. And these are, just to refresh our memory, Euler's sum of degrees theorem. That was number 25. Then there was draw an Euler circuit or path. That was number 26. Then there was draw a minimum duplication circuit or minimum duplication path. That was like on the homework last week. Then there was draw Hamilton circuits. That's like on the homework today. Then there was traveling salesman problem, the brute force. Then the nearest neighbor. Then the sorted edges. And then finally the, what we just did this morning, minimum spanning tree, sorted edges. In my opinion, these last 4 are all pretty easy. You have to know how to do it, but once you understand how to do it, they're pretty straightforward. The brute force is kind of a pain. It'll take you a few minutes to do it, but there's not a whole. I consider these 4 to be quite a bit easier than these ones. Sum of degrees theorem is pretty straightforward also. But does anybody have any questions about any of those? I hope that you have a fairly good idea about what kinds of questions I might be asking on each of these different topics. You should expect, as usual, the questions on the test will be similar to the homework questions. Yeah?
Could we possibly go over the sum of degrees?
Yeah, sure. So the sum of degrees theorem is sum of degrees theorem. This is Euler's sum of degrees theorem. It says in any graph, the sum of the degrees is always even. It's true. The sum of degrees in any graph is always even. Another way of saying that, so this is, maybe I should write this as kind of like two things here. One way to say it is the sum of the degrees is always even, and another totally equivalent way to say it is the number of odd degrees is even. This is maybe sounds a little bit more confusing, but this is another. Those are 2 equivalent ways of saying the same thing. The sum of the degrees is always even. Another way to say that is that's a number sign. The number of odd degrees is even. And this one, there was a homework problem about this last week about like my friends, and some of my friends are friends with each other, right? And I had described a scenario in which, Chuck has 2 friends, Patty has 1 friend, and the scenario that I described was actually impossible because if you added up all the degrees, it would have added up to an odd number, and that is impossible. This is the sum of degrees. Is that helpful? Yeah. It's a very sort of simple kind of fact about all graphs. Any other questions about any of these topics? I hope that everybody at least remembers what these things are. Yeah.
What's the MDC and MDP again?
Minimum duplication circuit and minimum duplication path. Yeah, that's the one where you double up some of the edges in order to make all the degrees even, or all except 2. We have about 20 minutes left. What I thought I would do, and I hope this is not too confusing, but these last 2 items will appear on the test, but they have not been on any homework assignment yet. So what I would like to do, I'm going to have one last homework assignment which covers these 2 things, but just because they're going to be on the test, I thought it might be helpful if I give you that homework assignment today. So this is a little weird, but we do have homework due tonight. And we also have another assignment, which I'm giving you today, which is not due today. So do the one that's due today, but also do this one, which is about the last 2 topics. Is that confusing? I don't know. But I'm going to give you this now. And we have 20 more minutes on the clock. I thought, this one, which is hopefully fresh in your mind, all about the sorted edges, I thought that we could just sit here and do this one now. I'm going to walk around and see how everybody's doing, and I would be happy to help out if there are things you're unsure about. And I'm also happy to talk about like the homework which is actually due today. We could, if you have questions about that one as I'm walking around, I am happy to discuss that also. Feel free to work along with your friends if you got any. This also, you can get a PDF of this on the website if you prefer it that way. I know some people like to do it that way. Actually, now that I mention it, I'm not sure I posted it yet, so that may not be true. So this, what I just gave you, is homework number 11, which will be due as usual on Wednesday, this time, Wednesday of next week. Now there is, just so that I don't anger anybody, there is an official rule. I don't know if you're aware of this. There's a rule that I am not allowed to make homework assignments that are due after the last day of class. This is a rule which I'm kind of violating here. So how about this? Let's just say between you and me, this is due on Friday, the last day of class, but it's totally cool with me if you give it to me on Wednesday, all right? So I'm not trying to encroach on your final exam preparation time. Ideally, you could just do it right now, although I don't know if 20 minutes is enough time for that. But it's due next Wednesday. I'll put that in quotes.